Okay, so from the previous lecture, yeah, Shabab, we talk about how we can compute integration or how we can approximate integration. And we said that we can solve the integration by different method or Newton codes format. But here we have different techniques to enhance the accuracy, otherwise by using single segment or by use a multiple segment. And so a single segment, we can use multiple segment here to enhance the accuracy of our estimation. As you can see, when we use a single segment, so usually we'll ignore significant area here under the graphs. And in this case, usually if the graphs contain curvature or contain peaks, large peaks or deep peaks. So in this case, using single segment, this will cause a huge error or significant error. So through this one, or to try to cover a maximum area under this curvature, so we usually try to use sub intervals. So if we use sub intervals like this one, so we can cover some of the area under this curvature. If we reduce the width of this interval, so we can cover more. Okay, so if we add more intervals or sub intervals, so in this case, this will make the computation or the computing is hard for us by using, for example, handwriting, but also by computer will be heavy. But here we can get good accuracy. If we look for good accuracy here, we can use more sub intervals. So, and also in the last lecture, we talked about trapezoid rule for a single segment, and we said how we can compute integration without direct computing of the integration by using the normal or an analytical solution. We can use this form of trapezoid rule. As we said, this is not just the width multiplied by the average of the height. And we use these to compute the integration of some functions. And after that, we found in some examples, like what we have in the textbook, the error here is very, very huge, it's around 89.5%. Because if we use straight line, so we will ignore all the area above this straight line. After that, we goes with the multiple, or we used multiple multiple application of the trapezoid rule. And this is one way to enhance the accuracy here. As we said, instead to have a single segment, we can use multiple segment. So in this multiple segment, you can see if we add multiple segment, the ignored area under the curve is reduced. So in this case, we can enhance the accuracy over here. And we did some examples for this one, for how many steps that we use. I think the last lecture we stopped at Simpson rules. Yeah. So what we have today we want to review the Simpson rules, two Simpson rules. After that, we will talk about Romberg integration. After this one, just we have here one example or two examples, and then inshallah we'll go with Romberg estimation that's help us to enhance the accuracy more. So here, as we said, Simpson third rule, it is an extension of trapezoidal rule by using the midpoint, because in trapezoidal rule we use point B and point A to evaluate the integration, and we use this is the average of these points multiplied by multiply this function by the width or the base. Here to increase or to enhance the accuracy, to have good accuracy, so we can use high order polynomial. One of these rules is use Simpson rule. Simpson rule is use the midpoint between A and B, and then as a result, because we already have the point A and the point B, so with the midpoint, so in this case, by using these three data points, can be connected to get a second order polynomial. Trapezoid rule, as we know, this is first order polynomial. So here we can get second order polynomial. Fourth order polynomial also can be used. And this we call this 3/8 Simpson rule. We'll come to this after this one. So the numerical integration method based on the second order and the third order Simpson rule can enhance the accuracy. We can use this one to enhance the accuracy. So in Simpson third rule, we integrate or we approximate the integration by using second order polynomial. 3 data points is needed to connect with the parabola. We integrate this one, and after that we can find the approximation of the integration. So this method is derived using Lagrange interpolation polynomial. So if you look for derivation, how we get this format, this is the, okay, where is this one? Yes, this is the form or the role for single segment. This is about single segment or single application of Simpson third rule. You can see here, or this one, this is more clear for you. This one at the bottom here. You can see if f sub t, that means second order polynomial, from a to b, take the integration of this second order polynomial. Here we have h over 3 multiplied by lower bound plus upper bound 4 multiplied by the midpoint. So this is the midpoint between a and b multiplied by 4. Okay, how we get this form? From this one, by using Lagrange polynomial. This integration, we represent the function in terms of second order polynomial. After that, by taking the integration of this term and substitute instead of x's by b and a, and then at the result we get this polynomial. Okay, so this will be these results. While here h is equal b minus a over 2. Okay, so this is how we can determine the integration of the function using this method, Simpson rule. So this is the first example. I think we go through this one in the last lecture. The distance covered by a rocket from 8 seconds to 30 seconds is given by this equation. Use Simpson third rule to find this approximation. So we found this one using Simpson third rule. Okay, so here we can use it eitherwise by using a single segment or by using multiple segment. Okay, so if we assume we use it only single segment, and this is the rule that we have here h over 3, the form, in our form here, we have h over 3, and h is equal b minus a over 2, so this term outside, it will be b minus a over 6. Okay, so here we have b minus a over 6 multiplied by f at a plus 4 multiplied by the midpoint plus f at b. So we just substitute by these parameters, f at 8, substitute by 8 instead of t in the function, and the midpoint is 19, substitute by t equal 19 in the function, and we evaluate the function at 19. And then this plus the function at 30, and we substitute instead of t by 30 in the function. So as a result, we get these three terms, the midpoint multiplied by 4. So, and this is what we have outside, this h over 3. So as a result, this will be our approximation by using Simpson third rule. If we have the true value or the exact value or the exact solution, this one, so we can compute the true error, and the error here is minus 4.38. I think you did this for trapezoid rule. How much you get, ya shabab, the error? I have your files here, but I did not create them. How much you get, ya shabab?
7.3%.
What's this? The percentage or the error?
The percentage.
7.3%.
Yes.
Yes, okay. You can see, ya shabab, when we use trapezoid rule, the percentage relative error is 7.3%. And if we compare this one with Simpson rule, and Simpson rule is 0.0396%. So here we can see how much we can enhance the accuracy just by adding one extra point. Okay, this extra point is not just the midpoint between both. Also, to enhance the accuracy more by using Simpson third rule, we might go with multiple segment. Instead of use only one segment, we can use multiple segment. So the accuracy of the single segment can be improved by dividing the interval into n number of segments in equal or with equal width, equally spaced intervals. So this method called multiple Simpson third rule. So we do the same what we have before, just we divided the interval to sub-intervals. After that, we apply Simpson third rule on the every segment. Okay, at every segment. So for example, we have here Simpson rule at this segment or at this interval, plus Simpson rule at the second segment, plus Simpson rule at the third segment. So this individual integration of the equation 6 is substituted by the single application. So this is the single application here. You can see this for the single segment, we have 3 over h over 3 f0 plus 4. This is the midpoint between f1 and 3 and for x2. And then we find for the second segment, and then we find it for the third segment. We apply Simpson rule or third Simpson rule in both and every segment. So as a result with this one, we can finalize with this form. So this is the composite Simpson third rule. This is the rule that we have it. You can see يا شباب this rule it's equal integration by using a multiple segment Simpson rule. It's equal h over 3 f0 plus fn. This is the last point. Here we have 4 multiplied by I. We take the odd numbers 1, 3, 5, 7, etc. Here we have n minus 1. Okay, this is fxi plus 2 multiplied by the even numbers. Okay, so here we have I, otherwise 2, 4, 6. Here we have n minus 4. Minus 2, sorry, multiplied by x5. So this is better for programming. If we need to do programming here, this is better for programming. This form is better for programming because here we have summing points and we can sort them easy. Just we find if we have certain data, just we compute or evaluate the function. I do evaluation here, for example, for the function at x0, what's the value? For example, 0. After that, I evaluate the function at x1. Okay, what's the value here? Evaluate the function at x2. Okay, so until xn, I find the values. Any values here, I will do it until f at xn. So what's the next step? I need this f0 and f1. This is the first two terms. Then I will take the even numbers. Okay, this is the even numbers. This is the odd, sorry. If I take the odd numbers, this is the odd numbers. If I have here also f at x3, so this is odd as well. Okay, so I will take the odd numbers, I will sum them, I will multiply them by 4. So I take the numbers for the even numbers. F at x odd, sorry, for example, first odd, f at x0, sorry, f at x1, and f at x3, f at x5. If I have these in my division here, if I have all these numbers, so I will take the odd numbers, I will sum them, and then I multiply them by 4, the odd. Then I will take the even numbers. For example, I have 4 here. I have f at x4, for example. So I will take them. I multiply these by, I will sum them, and then I multiply these by 2. Okay. How this is good? Because here you can see, ya shabab, here when we compute the midpoint, we have here the midpoint is 4 multiplied by x1. Here we have 4 multiplied by x3. Here we have 4 multiplied by n minus 1. So here the terms, the odd terms are multiplied by 4, while the even terms multiplied by 2. Okay, so here we have 4, and here we have 4, here we have 4. And the number of the segment here should be even. Okay, the number of the segment should be even. Okay, so this is the form of the multiple segment Simpson third rule. Here we use multiple segment Simpson third rule. So it's clear, Shabab, this form, just we apply application. So we need to apply this one. After that, we split them. So this is all these things, Shabab, as we said, this is used for programming. So this they try to develop the formula here to be suitable for programming as much as they can. So it is easy for programming. So this form, you can see all the forms that we have here. It's better for programming, but you can find another forms of Simpson third rule that we can see it is easy for calculation. This like this one. So let's take this example. Here in this example, use 4 segments Simpson third rule. So from the question we have here Simpson third rule with 4 segments. So in this case we need to use multiple Simpson third rule. To approximate the distance covered by the rocket from t again 8 seconds to t or b 30 seconds by the given functions. This is the integration and this is the function is given. So here we use 4 segment Simpson rule to find approximation of the value x. Find the true error E of t from part A. Find the absolute relative true error A at A from part A as well. So if you go here, this is the Simpson rule. If I pick the rule here, I'll pick the rule. Let's bring it from here. Okay, so this is the Simpson third rule for n segments. Okay, so as we know, h is equal n minus a, b minus a over n. This is h. So here we have 30 minus 8 over 4. Okay, so we have 30 minus 8 over 4, and this will become 4.5 by 0.5. So the question, it asks us to use 4 segments. So if it is 4 segments, that means we need to evaluate 5 points. Because the segment is 4 plus 1, the points we need is 5. We need to evaluate 5 points, the number of the points. So here we have the point, the first point at t0 or x0. So this is at 8, and we evaluate the function at this point, compute it, just we substitute in the integration and try to find the value of this one. And then the second one, or x1, it's equal, or t0 is t0. So t1 is nothing, just t0 plus h. This is equal t1. We use the step size. So this h, nothing, just the step size. So t2 h just equal t1 plus h. We use the step size that we have here, 5.5. So like this one, and t3 here, it's equal t2 plus h. So, and this is, we have here t4 or the tn. So we have 5 points now, 1, 2, 3, 4, 5. So we can find or evaluate the function when t equal 8. And also t1 is equal 8 plus 5.5, and this 13.5. So we need to evaluate the function at 3.5. And also we have t2, it's equal 13.5 plus 5.5. this equal 19. So here we need to evaluate the function at 19. And 3 is equal 19 plus 5.5. So we need to evaluate the function at 24.5. And this is fn, okay, at tn. So now we know the 5 points. So then we'll split them, odd numbers and even numbers. Okay, so this is even, this number is even, and these both are odd. So we'll compute them. After that, we'll take a sum of this odd, multiply this by 4, and the value of the even multiply by 2. So here, if we substitute in the form directly, you can see we have 3, this is b minus 8, 3 minus 8 over 3 multiplied by n, and then n4. So here, this is the x0, and this is xn. The value of the odd, this is the values of the odd. We take 4 multiplied by f at t1, and 4 multiplied by f at t3, because these odd numbers. Here, this is even. So even here, we have 2 multiplied by f at t sub 2. So after that, we just compute these parameters, evaluate here. We find this is the approximation. Okay, this is the approximation. Here in this approximation, we can compare it again with the true value that we have. Okay, if you want to compare this one, just if we look for the exact solution what we have before, so this is the exact solution, and this is the approximation. You can see here the error is almost minus 0.3 meters. If you compute the absolute relative true value or true error, so this is equal 0.027%. So also this method, if you compare this, as we said, when we use trapezoid rule, we have 7, I think, as you said, 0.3%. Okay, when we use single segment, how much we have? Yes, just remember. So we have this one, so when you use this one, so when we use a single segment, this is the error, 0.0396. When we use a multiple segment, so we get this error. Okay, so that means if we use multiple segment, we can enhance the accuracy here by reducing the value of the error. Okay, so step by step we can reduce the error. So if you want to see more how much we can reduce if we add more points or more segments. So this is the same example, but here we have more segments. We divided the interval to more intervals or sub-intervals. So here you can see this is the, when we use here Simpson with 2 points, 2 segments, because we use only the midpoint, we have a 0.396. This is Simpson rule with 4 segments. The error is 0.3. When we use 6 segments, you can see the error is reduced to 5 multiplied by 10 of minus 4. We have here these 8 segments. You can see it is 10 of minus 4. And here when we use 10, we have 0. It can be 4 zeros is multiplies by minus, or the error 0. You can see it is 0. The true error, sorry, the true error is 0, so all the numbers here is 0. Okay, so that means we get the exact solution. It's the same solution of the true. What's the true? Let's check it. The exact solution. Yeah, so this will be true because here 2 decimals. We use 2 decimals, so in this case, this will be 0. Okay, the error here will be 0 that way. So we can see, Shabab, if we go with multiple segment, in this case, we can enhance the accuracy. Okay, that means multiple segment, more, we divided the interval to small intervals. After that, we take the integration for these small intervals, and then we sum them. We sum them. Any question, ya Shabab, until here?
All clear.
Okay, so it's need practice يا شباب. You can try this one. This the table you have. You already have the table with this. We cannot have more examples. But what I advise you يا شباب, here you have 4 segment. Here you have 6 segment, for example. It gives you the solution. Try the solution from here. Change the question and make it 6 segments and try to practice this one. The segments must be even. You cannot take, for example, this is usually we take the number even numbers, the segment that we use. Okay, so here we can say this is 4 or 7, and sometimes they ask you otherwise to check them. Just check them by using, for example, 6. Try the same example with 8. Try the same example with 9, and you have the true or the correct value of the question, or the value of the approximation here. Just write if you get the same value, and then compute the error and the relative error. Okay, so in this case, we can, for example, practice more. The same thing is for the others. We have tables. Just use this table and try to practice more on this method. Okay, this is examples. Take one and try. Usually, like this, what we do. Okay, so this is about the Simpson third row. We have another method. We call this Simpson 3/8 row. Okay, this is another method. Should enhance also the accuracy more than the Simpson third row. So Simpson 3/8 rule, it's used a third order polynomial. Okay, that mean here we use 4 data points. So in this case, we need 3 intervals. Okay, we need 3 intervals. So this is the polynomial, third order polynomial. So that means if we have function, we want to compute integration of this function, f of t, and this t function or this function is complicated. So one way is to represent this function eitherwise linear equation or second order polynomial or third order polynomial. So if we can represent this function in terms of third order polynomial, so we call this Simpson 3/8 rule. How we can represent this one by third order polynomial? We can use Lagrange polynomial. So the interpolation topic, the topic of the interpolation and Taylor series is very important, and majority of the rules that we have is derived based on these 2 rules or these methods. So the basic, we start with Taylor series, and then we have interpolation. Interpolation if we have data points using. Okay, because what's the difference between interpolation and the least square? Interpolation, it's connected all the data points. So in this case, we'll have more accurate estimation because it's practice estimation, because the curve that you have will connect all data points that you have. And this is different from the least square. Least square, we try to minimize the error. And we not want, or we cannot ensure that this line will connect all the data. It's just we minimize the distance between the error and or the points that we have and the line or the fit line. But interpolation polynomial or polynomial or interpolation in general, otherwise Lagrange or a Newton divided difference, both they should connect all the data points that you have. So this is you will see this formula. No need to derive this one. We just needed to for practice. Okay, so for evenly spaced points here, we need the points to be even. And here we have the form. You can see the name. It comes from here. In this form, we have 3/8 multiplied by h. So the name Simpson comes from this form. Okay, so it is 3/8 h. We have the function at x0. 3 multiplied by x1. 3 multiplied by f at x2. Plus the function at x3. Okay, so this is the form that we have, but here we don't have examples. You can try the previous one. Just what we want here to we focus usually on the third order Simpson and and the previous method trapezoid roll. So if we do a comparison here, Simpson third roll and Simpson 3/8 roll have the same order of error. So the value of error here is O of power 4. If we compare this with trapezoidal roll has error of order h square. That means both Simpson third roll and Simpson 3/8 roll has the same order of error. Simpson roll requires even number of segments. So in Simpson roll, we need here even number of segments. Simpson roll, what's the difference between them? Simpson roll, it requires multiple of 3. Okay, multiples of 3. U3, 6, 9, like this one. So multiple of 3 segments. Here we have even, so we have 2 because they start with 2. We take the midpoint. You have 4 to compute the 2 midpoints, like this one. So here we need even number, but here we need multiple of 3 segments. So both methods, if Simpson methods requires evenly spaced data points. Okay, so this is the comparison, and this is the form for Simpson third order, and this is the h how you can compute it. Here we have h equal b minus a over 3. Also, there is available different type of Simpson method. We call them adaptive Simpson rolls. These methods usually it is adaptive or adjusted or modified to deal or to give more accuracy or to enhance the accuracy. And some of these methods, it's mixed between Simpson third roll and Simpson 3/8 roll. Some of these methods do mix in between these two methods what we studied before. For example, if we have one of these methods, it's called adaptive, and we have a list of these methods, adaptive methods for Simpson. Just this for your knowledge only. So here we have a mixed technology or mixing scheme. So here, if we assume we have n data points, so in this case we have 9 intervals. So one of these examples, they use, for example, the first 6 intervals use Simpson third roll, and the last third intervals they use Simpson 3/8 roll. So also there is another methods, advanced methods use Simpson method, but we focus here in the Simpson third roll and a little bit in the 3/8 roll. Okay, this is just for your knowledge to know. This is we not stop here. You can, if you want, for example, to enhance the accuracy further, you can go further than this what we have. Any question, Bob? Any question? So the last topic, what we have here in this unit is Romberg integration. Romberg integration, as we know, this is generally called Richardson extrapolation, and we are familiar with this. We studied this before in the integration differentiation or numerical differentiation. So what we have here, if you remember Richardson extrapolation, we just replace what we have in the form instead of d by i's. So we replace the derivative by integration. We'll use the same rule what we have it before. So the same idea, the same concept. So Romberg integration is one technique. It's designed to have or to enhance the accuracy. It's quite similar to trapezoid roll in sense that we use before ya shabab, if you talk about Richardson extrapolation, in the first column we use central divided difference, the first column, and we apply Richardson extrapolation and from the second column to the end. Here in Romberg integration, we apply trapezoid rule in the first column. And we apply Romberg integration from the second column to the end. Okay, so the same idea. So here it is quite similar to trapezoid rule. That means we apply trapezoid rule in the first column. Okay, and then we apply Romberg integration and the other columns. So it is generally, as we said, is called Richardson extrapolation. This method is used to estimate of integration. So we have two estimate of integration. So we have integration at hi, at integration at h1, and integration at h2, and h2 is half of h1. h2 just half of h1. The same thing is what we have in the Richardson. And this h1 and h2 is computed using trapezoid rule. Okay, here we have h1 and this is h2, and h2 is half of h1. You can see here h2 half of h1. So this h1 or I at h1 and I at h2 are estimated using trapezoid rule. So the values in the first column estimated by using trapezoid rule. So the estimation here with trapezoid rule, it gives us an error with order h of power 2. After that, we use these two estimation of the integration of order 2 to produce a new estimate of order 4. Okay, of order 4. So, and this new estimate, we call this Romberg integration. For special case, as we said, if h2 equal half of h1, so in this case, we finalize with this form. So we have the integration, it's equal or approximately equal 4/3 I at h2 minus 1/3 multiplied by I at h1. So this is the method like what we did before in Richardson method. So Romberg method, it's used trapezoid rule with sizes h/2, h/4, h/8. So this is the first column that we have here. So the first column of Romberg, we have the first column. We apply here in the first column trapezoid method. Okay, we apply trapezoid method in the first column. Okay, to find the first integration or the approximation of the integration with error of order h of power 2. After that, from the second column, for example, if you want to estimate the integration R11, so in this case, we apply Romberg algorithm. Clear يا شباب? So this method, it's applicable for single segment or multiple segments. It's up to you. So this is Romberg integration, Richardson extrapolation, the same things. So here in Richardson, we have here central divided difference, and here in Romberg, we have trapezoid rule. So the first column is nothing, just trapezoid rule with error order h square. After that, we can use the first order Romberg level. So we have here this order 4, and then second level will be order 6, order 8, and we go extra to the end. So as we go further by using Romberg integration, so in this case we can enhance the accuracy more. Any questions, Shabab? Any question? Okay, so let's talk about trapezoid rule in terms of recursive. If we want to do Romberg integration as a recursive, that means algorithms, how we can use this trapezoid rule as recursive. So what's the recursive version of trapezoid rule? So this is, we call this form is trapezoid rule recursive or recursive trapezoid method. So if we want here to estimate one interval, So in the table, you can see we have here R00. This means the first column or 0 column, 0 row. The first number here. R00, how we can compute this one? So here we apply the trapezoid rule directly, or by using this algorithm, we call that B minus A over 2 if at A plus if at B. Okay, because here we have a single segment. The second step, when we have two intervals. Okay, this is to compute now this value R10, this second term. Okay, this term that we have it here. Okay, so here we have two intervals. Okay, we have here two intervals. So in this case, we have H equal B minus A over 2. Okay, so by substituting here, what we have, so this is the form that we have. We substitute here in the recursive version the value of H, and this is, we have the value of H, and here we have B minus F at B plus F at A multiplied by half. So we finalize with this form. Okay, you can see we have here half of the previous estimation at R00. Here we update X, X0. Now this is X1 because it's X plus X0 plus H. So the value here is X1. Right, if this is X0, so this is X1 here. Okay, this is A plus H. Okay, so this is X2 if we add to H like this one. So this is the previous estimation, and this is this term we evaluate the function at the new point. The same things we can do it after that. We finalize with the logarithm. I will show you the logarithm later after these slides. If we have, for example, to compute R20, okay, so in this case we have 4 segments. Okay, and the 4th segment, it's given in this form, R20. We have here half of the previous estimation. This is H, the previous value. Okay, and this is the new value that we have. Okay, this is the new value that you have. So this is we can go to this logarithm. So logarithm is given in this form. This is the logarithm you can talk about. Okay, so this is the logarithm that we have. So here, this is that recursive Romberg method. We have here, this is the first one, R00. Anyone have a question here? Any questions, Shabab? Okay, so this is a logarithm or recursive Romberg method. We can compute R00 by this form. So after that, the value of H, it's equal this form. We have here H B minus A over 2 power N. So what's in here? We have it. So here we have N is equal to 2. After that, 3, 4, like this one, 2 power 3. So this is the value of N's that we have. So this is for the first column, and this is for the N columns. Okay, this is for the first column. This rest this number to compute this number, and to compute this number, and to compute this number. Okay, so here we have, for example, if we need here to substitute instead of N by 1, so here we have 1. So if this is 1 here, so this is 1 minus 1, so this becomes 0. Okay, and here you have 1. 1 minus 1, 0, so the order here is 1. Okay, so we just substitute instead of k by 1. So we have 2 minus 1. This become H. Okay, so here we have just summation half R00 okay, and h multiplied by this term. Okay, so that's what we have here in the recursive. Okay, so this we do this algorithm. So this is the algorithm as we said. So this is for the first number only. We have special role. This is the role for the first columns using the trapezoid role, and this is the Ramberg algorithm. And this is for better estimation. Any question, Shabab?
Doctor, if you want to calculate, for example, the nth, we need to calculate all the numbers before it.
Yes, if you want to find this number, you need to do this one because we use this like Richardson. We use this one to estimate this number. Okay. After that, we use this two number to estimate this number, and we use these two to estimate this one, and then we'll use these two to estimate this one, and then this one and this one to estimate this one. So if you want to estimate this number, we need to use the estimation before. Okay, what we did before, like this one. So this is based because this one, it's need these two numbers to estimate. The idea here, we use the previous two estimation to estimate a new one with better accuracy. And this number also, we need 2 points before. And this number, we need 2 points before. So like this one, you start like زي الهرم. Okay, reduce. Any question here, Shiva?
Okay, clear. Thank you, Doctor.
Okay, so what we have here, so this algorithm, I think it is easy to find. So this is the recursive method, as we said. So here when we have R00, R11, and how we can compute this for the first column. So the first column, we apply the recursive trapezoid rule. Okay. So if you take example here, so this is an example. Compute the integration of the function f of t is f of x is equal x squared. Okay. And here, for example, given the value h here, h is equal 1. So to find the first term, r00, as we know, so this is b minus a over 2 f at b and f plus f at a, and we just substitute here in this function when x equals 0, so this becomes 0. When x equal 1, so this is 1. So we have this multiplied by half, so this becomes half. So this is the first one, r00. R10 when we use half of h. Okay, so here we use half of the value of h. So we try to compute the value. We have here half multiplied by r00. So h here is 1, so the next step h will be half of h. Or h2 is half of h1. So here we have 1 over 2. Okay, and we evaluate the function at this one. Evaluate the function at a plus h. A is 0 plus half is 0.5. After that, we substitute, we get this parameter, and this is the evaluation of this function. So this term. So what we do now, we use these two estimation to estimate this one. Okay, so what we have in the second column, or we need to use Ramberg algorithm. So this is a Ramberg algorithm. You can see Ramberg algorithm. It's Rnm. It's equal 1 over 4 power m minus 1. This is the same thing as what we have Richardson extrapolation. 4 multiplied by Rn m minus 1 minus Rn minus 1 m minus 1. So here, if we need R11, so we have here m is 1, so we have here 1 over 3 multiplied by 4, so this will be 4 as 0 multiple, so this will be 4 over 3. We have here this term, R10 minus third R00. So here we have 4 over 3 multiply by the first estimation or the new estimation. This will be 4/3. Okay, minus this one. Okay, so we have here R00 is half multiplied by 1/3. So the new estimation will be 1/3 of the value of the integration. So if we want to enhance it also, the estimation more, so we can add more terms. Okay, so by reducing h again by half, so h3 is equal half of h2, because h2 is 1/2, so this become 1/4. So by using here the logarithm, here we need to use trapezoid rule to compute this one. So this trapezoid rule, the first column trapezoid rule. What we have from the second column to the left, this is Ramberg rule. Okay, Shabab, please distinguish between these. So we use this trapezoid rule here to find this value, and then we use Ramberg rule to find this one. Okay, so here if we have R20, you can see it's equal half R01 or 10 plus H, FA plus H plus FA plus 3H. Okay, so here we just substitute by the value. This is the value that we have half multiplied by the R10 plus the value of H 1/4 multiplied by the function A plus H, and H is 1/4. And in this case, we just substitute in the function that we have x squared to evaluate this value. This is plus A is 0 plus 3/4. We evaluate the function at 3/4 and we compute the value. And then we solve this one algebraically and we find this one, it is 11/32. So we're now doing this one. So by using this trapezoid rule and this trapezoid rule, we can estimate this one, the first order Ramberg rule. So this is the first order Ramberg rule. And then we'll use this one and this one to compute also the first order Ramberg rule. So now this is with h power 4. The estimation here, the order of h is power 4, and this is the estimation here of error with power 2. So if you want to also to enhance the accuracy more, for example, if you want to stop at R22. Okay, so R22, what's the value of R22? So it is the value here. So we can compute it like this one. Okay, so we can do it like this one. So this is the row 2 and this column number 2. If we want to compute it, so we compute it like this. So we need to compute here the value here R21. This is row number, you can see this is row number 2, 0, 1, 2, this is 0, and this is 1, and this is 2. So here this is R21, this column 0, okay, and this column 1. R21 is this number, 1/3. So we just here substitute in the logarithm of Ramberg logarithm. We have here n is equal to and m is equal 1. Okay, so we find the value here is 1/3. After that, we use the previous estimation. If you substitute here again in the logarithm, you have n2 and m2. So you have here 1/4 square minus 1. Here you have 4 square multiplied by R21 minus R11. And this is R11 here, and R21 is this one. So we'll use these two to get a new estimation with order 6. Okay, so in this case, we can do these algorithms that will help us to enhance the accuracy. Any question? Any question? A question, ya shabab, I will go to next unit after this. Because I have another example only after that, I will go to the next. It's clear this example? Clear this one? How we do it?
Yes.
I hope that, inshallah. Okay, so when do we stop? This is the question. How many iteration we need to do? Or when we do stop? So usually how we stop here is dependent on otherwise in the question. If the value, for example, n Rn less than Rn n minus 1 is less than or equal the error, we stop. So here we can stop if Rn, for example, this is R22 minus R2, example 1. Okay, so the absolute value of this one is less than or equal the error, the stopping error. Here we can stop. Or we can ask you how many iteration like before. This is the easiest way. After we told you, for example, stop or we compute this value, for example, R44. So in this case, we give you the number of the steps that you need. We give you a table and you know this value. So here you stop at this one. For example, in the previous example, we stop at R22. Okay, so this is another method to stop. This is the stopping criteria that we have. Otherwise, we compare the new estimation and the previous estimation and the same row. If the new estimation minus the previous estimation is less than the error, so in this case we stop. Or the other criteria by using from the question. Usually we give you like this one, evaluate the function R22 or R33 like this. So in this case we need, or you need to stop at this point. Just fill the table. You have the table in the exam like this one. You have the table and you will have this equation that you have. All these forms will be given, inshallah, Ramberg method. Okay, just practice. As we said, this one a special case, and after that we have these forms. This for the first column only, and this is for the other columns. So this one, trapezoidal. Question? Any question? So let's take these last examples that we have in this unit. After that, you can go through this one, the rest. As you know, ya shabab, when we use this example from the textbook to solve the function or to find the integration or to evaluate the integration of this function using trapezoid rule, and we used before 1 segment, 2 segment, and 4 segment, and this is the evaluation of trapezoid rule. Okay, so when we use first segment, 2 segment, and 3 segment. If you want, for example, to enhance the accuracy, as we said, okay, so we want to use this one, for example, R00 and R10 to get a new one, for example, R11. To enhance the accuracy, we need to get R11. So here we can use this rule, Ramberg rule. It's equal 4/3 R10 minus 1/3 R00. So in this case, we can get R11. So this is the new estimation. Okay, so in this case, we can reduce the error. You can see the error before we have 34.9, and now we reduce the error to 16.6. Also, we can use R20 and R10 to get R21. So we have here R20 is 1.848. So this number we multiply 4/3, 1.4848 minus 1/3 by R10. Okay, so we get the new estimation here. And if we compute the error, you can see the error is reduced. Now we have the error is 1%. So if you want to enhance the accuracy more, so we can use another columns or more accurate things. So we can use to enhance the accuracy or the integration. We can use 3 trapezoid estimation. These 3 estimation. We use 1, 2, 3 now. As a result of these 3 estimation to get a new one. These 3 estimation, trapezoid, and trapezoid, So in this case, we can use 3 trapezoid rule to estimate one with order 4. Okay, so these two improved estimation can be combined together to improve the accuracy in order h of power 6. How we can do this one? So this is the form of h of power 6. h of power 6 is nothing just 16 over 15 im minus 1 over 15 I. Okay, where im and ii are more and less accurate estimation. Okay, so im is the maximum accurate estimation and il is the lower estimation. If you want to enhance the estimation more, for the third column, to get estimation with h power 8. Okay, so in this case, we can use this algorithm. Integration is 64 over 63 im minus 1 over 63 ii. So you can know this one. This is now for the column. If you located for this columns, we have here. This is the column. We use this one. 64 over 63 im multiplied by 1 over 63 ii. So it's used for this one. Okay, if you want to estimate for this one, we use the previous one for h6, and this is for h4 or this algorithms. Otherwise, I will give you these forms. Inshallah, I will share with you the handouts before the exam. Okay, otherwise I will give you these forms, the algorithms here. Where is the algorithms? These algorithms, or I will give you this one. Easy to multiply these integrations. I will see later what I will give you. Okay, so this, you know, this is for the next estimation, and this for the brief estimation that we use. So this is, as we said, this is the trapezoid rule. This table, I think, is better for you. Yes. This table here we have trapezoid rule. This is the first level of Ramberg estimation. This is the second level of Ramberg estimation, and this is the third level of Ramberg estimation. Or I can give you this one, inshallah, during the assignments. Okay, so this is how we can estimate the error by using high order methods. By using this one, for example, level 2. Okay, so we use what we have the previous estimation to estimation before of order h4. So to get a new estimation of order 6. This is the what we call this. This is Ramberg estimation, but here we use this for algorithms. You can see what's the difference here. So you can see here, this is, we can notice from this one, the coefficient here and this one, in each equation, it's added by 1. Okay, so we add 1 here. If you can see before we have R0, R10, R like this one. So here we add 1, 1. So this is for recursive. We call this recursive, and this is for better programming. This is for programming. For programming, we use this rule. Okay, this is for programming. It is easy, and instead to have zeros here, R0 and R10, like this one. Just we add 1. Okay, or add up to 1, for example, here. So now to becomes, we have all the table in terms of logarithm. So we have here integration in terms of j and k. Okay, and after that we can compute it by using this one. So we can do it this using a logarithm to enhance the accuracy. We have here this one. We have j, the value is 1 and k is 1. And you have here, this is a logarithm that you have. Just we substitute here as a code or represent this as a code. And also we use the error here. We can use it by the same code that we have. Okay, so this is just a recursive Ramberg integration. Don't confuse between this table and what we have before. This table is for algorithms. Usually we use it like this one. Or you can also use this for calculation, if you want. you can see here we just add, instead we have column 0, so we start from 1. Okay, so we add up to 1. Yes, تفضل.
We have 2 methods now for rendering.
Which one?
We have 2 methods.
Yes, yes. Usually we'll work on this one. I told you this is and Romberg. You will use this method. This table usually I will give you. Okay, if I give you the second one, I will give you the table. I will give you the logarithm. But this is usually what I give. This Romberg table, and this is the table, and this is the codes for this one. Okay. Okay, so this, as I told you, this is usually it's used for computer base. Here we replace the zeros by ones. We add ones. Okay, so this becomes as a logarithm, and it's easy for implement as a logarithm. You can see this is the logarithm that you have. This is, for example, MATLAB code from Romberg method. We have this the function, and this here the function, and the foundation here, and this is the level. The number of the intervals defined here. Trapezoid rule is used, and after that this Romberg, you can see how you can use it. This is the code. Okay, this is the code how we use it here. So this especially it's developed as a logarithm. Okay, shabab. So usually we use this one, this table for calculation. For calculation, this is the form. Any question, shabab?